Hey there, science fans. Have you ever looked around and wondered what makes up everything you see? Well, get ready to unlock a universe of knowledge with the periodic table, your ultimate guide to the building blocks of matter. The periodic table is like a giant, organized chart that lists all the known elements in the universe. Elements are the simplest forms of matter, and they can't be broken down into anything simpler.
Think of elements like ingredients in your favorite recipe. Each one has unique properties that make it special.
The periodic table doesn't just list these elements randomly, it arranges them in a specific way that reveals fascinating patterns and relationships between them. This organization helps us understand how elements behave, react with each other, and even predict the properties of elements yet to be discovered. So, buckle up, science explorers. We're about to embark on an exciting journey through the incredible world of the periodic table, where we'll uncover its secrets, explore its history, and discover its impact on our lives. Get ready for an adventure in the amazing realm of chemistry. Our journey begins in the mid-1800s with a brilliant Russian chemist named Dmitri Mendeleev. Mendeleev was on a mission to organize the known elements, which were a bit like a jumbled puzzle back then.
I noticed that when elements were arranged by their atomic weight, certain properties seemed to repeat periodically. Imagine a line of friends where every other person has curly hair. That's periodicity.
Mendeleev used this observation to create his first periodic table, leaving gaps for elements he predicted would be discovered later. And guess what? He was right.
Years later, I made a crucial discovery. I found that each element has a unique atomic number, the number of protons in its nucleus. This realization led to rearranging the table based on atomic number instead of atomic weight, giving us the modern periodic table we use today.
The periodic table is a testament to the power of observation, organization, and a little bit of scientific intuition. Now, let's get to know the layout of the periodic table. Imagine a grid with rows called periods and columns called groups. Each period represents an increasing energy level for the electrons orbiting the atom's nucleus. Think of it like floors in a building with electrons as residents. Elements in the same period have the same number of electron floors or energy levels. Groups, on the other hand, gather elements with similar chemical properties. Elements in the same group tend to react similarly because they have the same number of valence electrons, the outermost electrons involved in chemical bonding. But wait, there's more. The periodic table also has blocks based on the type of orbital where the last electron is added. These blocks are named S, P, D, and F, each with unique characteristics. Think of them as neighborhoods within our element city. Understanding the structure of the periodic table helps us navigate its vast landscape and uncover the secrets hidden within each element's square. The periodic table isn't just about organization, it's about relationships. Elements are grouped into families based on their properties, much like how families share similar traits.
On the left side of the table, we have the metal's shiny, malleable elements that are good conductors of heat and electricity. Think of everyday heroes like iron, copper, and gold.
On the far right, we have the non-metals, elements that are usually dull, brittle, and poor conductors. These include essential elements like oxygen, nitrogen, and carbon, and then we have the metalloids, the in-betweeners. These elements have properties of both metals and non-metals, making them versatile for various applications. Silicon, for example, is a metalloid used in computer chips. Understanding these broad classifications helps us predict how elements might behave in different situations. Section 5, Element Trends. Predicting the unpredictable. One of the most remarkable things about the periodic table is its ability to predict trends in element properties. These trends, like atomic radius, ionization energy, and electronegativity, help us understand how elements interact and form chemical bonds. Atomic radius describes the size of an atom. As we move down a group, atomic radius increases because we're adding more electron shells. However, as we move across a period, atomic radius decreases because the increasing positive charge in the nucleus pulls the electrons closer. Ionization energy is the energy required to remove an electron from an atom. It generally increases as we move across a period because the increasing nuclear charge holds onto electrons more tightly. Electronegativity measures an atom's ability to attract electrons in a chemical bond. It generally increases as we move across a period because atoms with higher electronegativity are closer to achieving a stable electron configuration. These trends, along with others like electron affinity, help us predict how elements will behave in chemical reactions. Section 6, the periodic table superpower, predicting the future of chemistry. Now here's where the periodic table gets really cool. It can predict the properties of elements before they're even discovered. Remember those gaps in Mendeleev's original table? He used trends to predict the properties of the missing elements, and he was incredibly accurate.
For example, I predicted the existence of an element I called eka-aluminum, which would have properties similar to aluminum.
Years later, scientists discovered gallium, which fit Mendeleev's predictions perfectly. This predictive power is what makes the periodic table such a valuable tool in chemistry and material science. By understanding the trends, we can design new materials with specific properties. Section 7. Pushing the limits, superheavy elements, and the island of stability. Scientists are always pushing the boundaries of the periodic table, creating new elements through nuclear reactions. These synthetic elements, called superheavy elements, are located at the bottom of the table and have atomic numbers greater than 104. Superheavy elements are extremely unstable and decay rapidly, making them difficult to study.
However, scientists believe there might be an island of stability, a region on the periodic table where superheavy elements are more stable and could exist for longer periods.
The search for the island of stability is a hot topic in nuclear physics, and discovering these superheavy elements could lead to new technologies and a deeper understanding of the universe. The development of the periodic table is a testament to the collaborative nature of science. Countless scientists have contributed to our understanding of the elements and their relationships.
We've already met Dmitri Mendeleev and Henry Moseley, but many other brilliant minds deserve recognition.
Antoine Lavoisier, for example, is considered the father of modern chemistry for his work on classifying elements and defining elements as fundamental substances.
Jöns Jakob Berzelius developed the modern system of chemical symbols, making it easier to represent elements and their combinations.
And Marie Curie's groundbreaking research on radioactivity led to the discovery of polonium and radium, expanding the periodic table and our understanding of atomic structure. These are just a few of the many scientists who have shaped our understanding of the elements and the periodic table. The periodic table isn't just a chart on a classroom wall. It's a fundamental tool used in countless fields, from medicine to engineering.
In education, the periodic table helps students understand the building blocks of matter and the relationships between elements. In industry, the periodic table guides the development of new materials, from lightweight alloys for airplanes to high-performance ceramics for electronics.
In medicine, radioactive isotopes are used in imaging techniques and cancer treatments. Researchers rely on the periodic table to understand chemical reactions, predict the properties of new compounds, and develop sustainable energy solutions. The periodic table's impact on our world is vast and continues to grow as we unlock more of its secrets. The periodic table is more than just a chart of elements. It's a testament to the power of human curiosity and the pursuit of knowledge. It's a reminder that the universe is governed by patterns and relationships waiting to be discovered. From its humble beginnings as a way to organize the elements, the periodic table has evolved into a fundamental tool that shapes our understanding of the world around us. Its predictive power has led to countless discoveries and innovations, and its influence continues to grow as we explore the frontiers of science. The periodic table is a symbol of the interconnectedness of all things, a reminder that even the smallest building blocks can have a profound impact on the universe. As we venture further into the 21st century, the periodic table remains a vital tool for scientific exploration. Scientists are constantly pushing its boundaries, synthesizing new elements, and exploring the limits of matter.
The search for the island of stability continues, promising to unlock new possibilities in nuclear physics and material science. Researchers are also investigating exotic forms of matter, such as quark-gluon plasma, which could reveal even more fundamental building blocks of the universe.
The periodic table will continue to evolve as our understanding of the universe deepens. New discoveries will refine our knowledge of element properties and potentially lead to new trends and patterns yet to be imagined. The periodic table is a testament to the ever-evolving nature of science, a reminder that there's always more to learn and explore in the vast and fascinating world of chemistry.